These are 5 aspects of Earth's atmosphere, put together into a surprisingly whole, as it were. Anyhow. These pieces have been published separately on YouTube. When I realized how beautiful a story they told when combined, I simply did so. Dusted off, re-recorded in better quality, and adapted to the audio medium. First up, St. Elmo's Fire. Hi, my name's Alex. I've argued enough for a lifetime. Put your headphones on, sit back, relax, and enjoy your commute or whatever else you're really doing right now. Good night to those of you who use my content to fall asleep. In addition, please share and like or give a thumbs up or do whatever one does on the platform you use to consume content like this. Doing so will help me a lot. Thanks. Have you ever heard about St. Elmo's Fire? It is rather rare, and truth be told, if you do know about it, chances are you may regard it somewhat uncertainly, as either tale or reality, not really knowing whether it is real or not. Well, it is just as real as it is rare. The physics behind it is not even that much of a mystery either. The expression to look for is field emission, quote-unquote. An explanation of which can be found in a rather well-written article at Wikipedia. The idea is that an electrostatic field can draw electrons out of the pointy end of a conducting material. Boats with masts are the usual places of observation for this phenomenon. Such masts have not always been made out of metal. Wood, that's what masts were made out of when St. Elmo's Fire was first spoken of and written about several hundred years back. Wood is not a conducting material. Yet, during a thunderstorm or during the build-up to one, the air may get so electrified that this doesn't matter. Remember, there are very few absolutes in physics. Conducting materials have a resistance, and non-conducting materials do still have some free electrons. The higher the energy, the more of these there are. This brings us back to the thunderstorms. If they are big, and I mean really big, the electrification of the surrounding air, that is, the electric field in it, may just be enough to scare some sailors. Lightning without thunder. I will start by mentioning that this particular physical phenomenon's name is made for lovers of weird acronyms. SPRITE. Stratospheric Mesospheric Perturbations by Intense Thunderstorm Electrification. Good one, eh? There are oodles of good pictures and videos everywhere on the internet. Search for SPRITE and Transient Luminous Event. So, what are sprites? I think the best way to approach their nature is by beginning at the ground or close to it. When there is a thunderstorm, the cloud itself is electrified with electric charge separating within the cloud, ions at the top and electrons at the bottom. Charge separation means there is an electric field inside the cloud. This is not necessarily a stable configuration, and when the electric field in the cloud becomes too strong, the atmosphere around the cloud may be electrified as well, and electric discharges can happen. The electric discharges we see most often we call lightning, or more precisely, cloud-to-ground lightning. When these happen, there is another electric field, a strong one too, between the cloud and the ground. One should not use a word like this about a physical system, but I will do it anyway. During a lightning event, the atmosphere is plainly weird. It looks weird, behaves weirdly, and weird stuff happens. If the lightning fulfills certain, not yet quite known conditions, the electric fields in the cloud and between the cloud and the ground somehow reconfigure themselves to result in another intense electric field somewhere above. This new electric field may, in fact, reach far above the cloud. If these flipped upwards electric fields are strong enough, electric discharges will happen there too. Those high-altitude discharges are called transient luminous events because in some ways they are lightning and in some ways they are not. As I mentioned, it is all just a wee bit weird. There are a great many types of transient luminous events, such as elves, gnomes, trolls and others, but the most prominent ones are the sprites. Vertical extension up to 60 kilometers. Duration a few milliseconds. I hope I will see one before I die. Google Earth can't show you planetary waves. Sometimes when water vapor content in the Earth's atmosphere is measured from above, strange structures appear at around 30 or 60 degrees latitude north or south. Looked at from above, these structures often resemble two-dimensional projections of ocean waves. In one respect, they actually are similar. They are waves, which can break and form vortices, as they are called technically. With an ocean wave, a surfer can ride through such a vortex. These wave structures appear because a jet stream is subject to the Coriolis force and begins to meander. Very often, high-altitude winds drain the jet stream of the energy required for the meandering. Sometimes they do not. Then, the meandering will cause a succession of alternating high-pressure and low-pressure volumes in the vicinity of the jet stream. Alternating high-pressure and low-pressure volumes, which are coupled, are called pressure waves, of which these so-called planetary waves are the ones with the largest wavelength of sometimes more than 1,000 kilometers or more than 600 miles. When I speak about coupled volumes, I mean that they influence each other. This being the Earth's atmosphere, the interaction between adjacent low and high pressure volumes may not be described easily, and mathematical equations have to be applied to the real-life situation. Now, you may have already noticed what I think, but let me also mention here that mathematics is a wonderful tool if applied on the background of proper expectations. And that's the thing. If you don't want to, it's perfectly acceptable to just realize the parallels between ocean waves and the largest atmospheric pressure waves there are, planetary waves. Noctilucent clouds. Noctilucent clouds are middle atmosphere phenomena connected to icy particles of meteoric origin, which occur exclusively during the summer months and exclusively in the polar regions of Earth. Why? Because the respective altitude, that is 80 to 90 kilometers above ground, is coldest in summer, such that ice can crystallize onto meteoric dust, despite there not being much water in the air to begin with. This raises some questions. Why do we even see these clouds? Should ice not be transparent? Yes, ice is virtually transparent. However, depending on the purity, thickness and structure of the icy particles, at least some light is scattered or reflected. Less than 0.1% of the incident sunlight is scattered by noctilucent clouds. which means that the clouds are only visible under rather special circumstances. In order to see what little light there is, one has to have a night sky above the cloud. Yet the sun cannot be so far below the horizon as to no longer illuminate the icy particles. In other words, noctilucent clouds are essentially twilight phenomena. It doesn't stop there. Why would it be so cold? In the summer of all times. The temperature in the middle atmosphere is connected to pressure waves generated in the lower atmosphere, which travel upwards and lose most of their energy at noctilucent clouds' altitudes. You can sometimes see these waves in fishbone-like structures in the noctilucent clouds themselves. The energy lost is used by nature to drive air away from the summer pole, thus creating a large and almost permanent low-pressure volume. In this volume, the temperature can drop to minus 140 degrees Celsius. Permanent is the wrong word, strictly spoken. For when the seasons change, the pattern of pressure waves changes too, and the wind at noctilucent clouds' altitudes changes direction. Also this, due to what is called pressure wave driving, quote-unquote. Don't ask me to explain pressure wave driving, by the way. The explanation lies in mathematics, and gaining knowledge by means of mathematics is a completely different story, which I am sure we will have to come back to eventually. Stop blaming the weatherman. Science is about curious complexity in which you can get lost, so we look for steadiness, things that don't change, like energy for example. The total energy of a physical system doesn't change no matter what. That's not a difficult thought, at least it doesn't sound threatening or something like that. Energy doesn't change, that's it. Is it difficult? Well, let's talk about the weather. The quality of today's weather forecast is awesome. This has a lot to do with what's called numerical methods, approximations whose strength is directly connected to the capacity of our computers. It's also highly dependent on brilliant meteorologists who know their maths well. In order to predict the weather, many different pieces of information need to be put together. Wind speeds and directions, temperatures and temperature gradients, humidity, and many other things. And that's okay. We can measure that stuff with weather stations, both on the ground and up at higher altitudes. We can build towers and release balloons, use planes and even sounding rockets or satellites to get our data. Because we are also forced to take into account stuff like, Sahara sand being transported all the way to the Caribbean, then along the Northern American east coast into an airstream running over Iceland towards Europe. These are winds on a truly global scale, which vary in strength and direction not only with altitude, but also with the seasons. Now, if you had to guess, would you think that there is a lot of weird small-scale stuff going on at the edges of these global winds? Air moves the way it does, at every scale, in 3 dimensions, at different temperatures and pressures and whatnot. I mean it. For years I worked at Andøya in the north of Norway, for example. There, the strongest winds usually come from the west or southwest in Arctic hurricanes. What's weird is that those winds tend to be strongest on the lee side of one particular mountain range on the island. They close the road there for a while every winter, and still there's always a car or two that manages to get blown off the road. Think about that for a second. Then think about how there may be a layer of increased humidity up in the air somewhere. Such layers absorb a lot of infrared radiation from the Earth's surface. They tend to warm the air a little extra in them and around them. There may also be a pressure wave propagating through the area, losing part of its energy and warming the air just a tad more by doing so. There may be the thermics eagles use to soar up high, and a host of other small and big stuff. Shall we continue? Well, let's imagine we sit behind a rock in a valley on the lee side of a mountain in northern Andøya, checking the cell phone for a weather forecast. Do you believe me when I say that weather's complicated? It's tempting to complain about the weather forecast. I mean, this shouldn't be that complicated. One place there is low pressure, the other place there's high pressure. Nature likes to balance things, so air flows from one to the other, influencing temperature and everything else. We call that wind. See, the single processes are not difficult. Putting all the pieces together now, that's something we don't have the capacity to do, honestly. To be able to make near-perfect weather predictions, we should calculate the movements and interactions of every air molecule. Don't count, the answer's 44 zeros. Who's got time for that? Before we are finished with that calculation on today's fastest supercomputers, the Andromeda Galaxy will collide with the Milky Way. We're talking billions of years from now. Whenever things are like this, scientists talk about chaos, not randomness. In chaos, there are causes and effects. In randomness, things are, well, random. How do we find out about chaos? By trying to find regularities, which make the whole thing more accessible. And yes, there are regularities in the natural chaos surrounding us. For example, something called self-similarity. A self-similar object consists of stuff that looks like itself, just smaller. Is that like finding order in chaos? No. It's the answer to the question of what is constant. In this case, it's a property of the physical system itself, which propagates through the whole process. Sounds weird? No worries, just take a look at lightning. If you stare at a picture of it for a while, you'll see some structure there. But it's hard to put your finger on it, right? What about tree branches? The very structure is our constant, and if you're interested, you can do maths with it too. The search term? Well, self-similarity. Weather's like that too. Well, no, but yes, it kinda is. At least in maths and in principle. Weather's chaotic. It is, however, not straightforward to approach nature's doings like that. We're not going to go into detail here, but realize this. Meteorologists, those who know most about the weather and climate, are best at tackling chaos. How do they do that? By taking all information possible into account, processing it through the right equations and developing these equations further and further as we see more and more through the chaos and gain more and more computing power. Supercomputers have become and still become more and more powerful. This allows for the equations to become more and more complete, and this means more exact. However, exact in the way we use the word in daily life, these equations aren't. It's quite possible that we will never have exact maths to describe the weather. For at the end of the day, chaos may very well just be nature's natural state. Thanks for staying with me to the end. Join me on socials and YouTube, or check out kindnessthrough-knowledge.com to find other ways to connect and work together. See you next time.